Hi, everybody. My name is James Bullock, and I'm the Dean of the School of Physical Sciences, and it's going to be my great pleasure to sort of play MC and host to tonight's just wonderful talk. We're very excited to have Professor Sam Ting here tonight. This is the 7th annual lecture honoring the memory of Fred Reines, who is the founding dean of our School of Physical Sciences and a real visionary in particle physics and means so much to the history of this campus at UC Irvine. And we'll say a few more things about Fred Reines later on. What I'm going to do now is introduce the introducer. But we're very honored actually tonight to have our provost, Hal Stern, here to do an introduction. Hal Stern is the provost and executive vice chancellor of the University of California, Irvine. He's also a chancellor's professor in the Department of Statistics. Provost Stern previously served as the founding chair of the Department of Statistics at UC Irvine and the dean of the Donald Bren School of Information and Computer Sciences. He then became the vice provost for academic planning at UCI before becoming the provost. He has held faculty positions at Iowa State University and Harvard University. And within the field of statistics, he's known for his research on Bayesian statistical methods and for collaborative projects in the life sciences and social sciences, among others. He's a fellow of the American Association for the Advancement of Science, the American Statistical Association, and the Institute for Mathematical Statistics. He has degrees from MIT and Stanford. Welcome, Provost Stern.
Thanks, James. You were supposed to get the short introduction, not the long introduction. It's great to see all of you. Thank you for being here this evening. I'm pleased, on behalf of the university, to welcome Professor Sam Ting and his wife to visit us for a few days. We're really, really grateful for that. I'd like to thank James, Dean Bullock, and Professor Jonathan Fung, who you'll hear from shortly, for being the organizers and leading this effort to bring Professor Ting to visit our community. I also want to thank several members of our UCI Foundation trustees. They're major supporters of the campus in a lot of different ways, and they're here tonight with all of us to enjoy the event. So thank you all for being here. We appreciate it. Like all of you, I look forward to hearing more from Professor Ting and less from me. So I'm going to be brief here. But I've been asked to say a few things about UC Irvine for those in the audience who are not necessarily members of our community. I usually tell people the provost and executive vice chancellor, nobody really knows what that means. I'm the chief operating officer. Okay, so that's my job. UCI, a relatively young institution, founded in 1965, and has had a remarkable ascendancy among American research universities. UCI now has 14, soon to be 15, academic units, and also a premier academic health center in UCI Health. We now have 37,000 students, about 29,000 undergraduates, and 7,000 graduate students. And UCI is Orange County's largest employer, just ahead of Disneyland. And I like to note that we are also the second happiest place on earth, but we're catching up. We're catching up there too. So. Okay. Our student population is incredibly diverse. It's a point of great pride. UCI is designated as a Hispanic serving institution by the Department of Education and as an Asian American, Native American, and Pacific Islander serving institution. One of very few universities in the country that have both of those designations. So with this large, diverse student population and fantastic student outcomes, we take great pride in the fact that the New York Times identified UC Irvine as the college doing the most for the American dream. Along with these educational successes, UCI is one of 66 universities that are members of the AAU, the Association of American Universities. These are America's leading research universities. And UC Irvine was the youngest university at the time that it was admitted. It got to that level so quickly. In the most recent year, across a wide range of the sciences, arts, and humanities, we received nearly $600 million in contracts and grants to perform research. This is double what it was just 7 years ago. So a remarkable period of growth. Of note in the School of Physical Sciences, who's hosting us tonight, two research centers funded recently by the Department of Energy to deal with different aspects of climate change. One on making solar energy more efficient, the other on carbon capture. So this is a high priority for the school and the campus. And as a last critical point that everyone must know, we have the most beloved mascot in all of higher education, Peter the Anteater. So I want to thank you all for being here, and I want to turn it back over to our MC, Dean Bullock, so we can enjoy the rest of the evening. Thank you.
Thanks so much. That's great. And I'm going to try to do my best to not be a dean and talk too long about the school here. Instead, I want to focus a little bit on Fred Reines. Fred was the founding dean of our school, and I think set a tremendous example for all of us that we're all working towards today. You may know that he won his Nobel Prize for discovering the neutrino. There were many people back in the day who thought the neutrino was a particle that could not be detected, and Fred Reines set out to do just that, partially motivated by the fact that people said he couldn't do it. And I think that kind of undeterred spirit is really with us. It's in our ethos here, trying to do hard things that maybe other people think can't be done. I could talk on and on about the amazing work going on right now in the physics department in particular, and all the other departments in our school. And if you'd like me to do that, please pull me aside at the reception, and I will do that as long as you want. But I think you can learn a lot from focusing on individual faculty members, and that's what I want to do because Professor Jonathan Fang is about to introduce Sam Ting. I think it's a fact that I would not be at UC Irvine if it wasn't for Jonathan. I don't know if you know this, Jonathan, but I remember interviewing here and being so excited that I got to talk to him as an assistant, potential assistant professor, and it was one of the reasons why I knew this place was great. I didn't know all about the rich history then. All I knew was Jonathan was here. And he is, in fact, fantastic. He works at the interface of physics and astronomy and explores deep connections about the cosmos and particle physics. His research spans topics from cosmology to nuclear physics. And most relevant maybe for tonight's talk is he's really the founder and now co-spokesperson of the phaser experiment at CERN. Which is amazing experiment that's looking for physics beyond the standard model that's, I think going to push new boundaries. He has degrees in mathematics and physics from Harvard, Cambridge, and Stanford. He joined the faculty in 2002 and recently was named a distinguished professor in 2021, which is a meteoric rise. He's been recognized in awards from the National Science Foundation, Sloan, Guggenheim, Heisen-Simons, and Simons Foundation. And you'll read about him all over the place, all kinds of public outreach. He really does it all. So with that, you're about to hear from someone awesome who's going to also introduce someone awesome, Jonathan Fang.
All right, well, thank you so much, James, for that very kind introduction. So it is my great honor to be able to introduce our speaker tonight, Professor Samuel Ting, the Thomas Dudley Cabot Institute Professor at MIT. If I look back through my emails, I see that the first time we invited Sam to be our Reines lecturer was in the fall of 2019, and we expected him to very shortly come to our campus and be the Reines lecturer. Well, you all probably know how that turned out. It's really entertaining reading emails from yourself from 2019 because you realize, well, you have no idea what's going to happen pretty soon. But I'm so grateful that Sam was kind enough to continue to consider our invitation, despite it being postponed and postponed and postponed again by COVID, and that we are finally able to welcome both him and Susan here today for an exciting week of events, kicked off today, of course, by this wonderful lecture. Sam grew up in China in a time of great turmoil. It was marred by the Sino-Japanese War and the Chinese Civil War. Eventually, he and his family moved to Taiwan, I think he was about 13 or 12 at the time, where he was finally able to attend school regularly. He then decided to come to the US for college, ending up in Ann Arbor, Michigan, with about $100 in his pocket and little proficiency in English. Despite this, he obtained his bachelor's degree in 3 years, and then his PhD in another 3 years. And then, if I just skip ahead just a little bit, but actually not too much, surprisingly, in 1974, he and his collaborators discovered the J particle and the charm quark, which is a new form of matter. For this, he was awarded the Nobel Prize in Physics in 1976, and several years ago, Sam joined that small and very elite group of scientists who have been Nobel Prize winners for more than half of their lives. Sam has made many other important contributions too, but let me just say a few more words about the charm quark, because I'm a particle physicist and it's an amazing thing. Discoveries of new particles come in sort of two flavors. There are those where the indirect evidence has been building for a really long time, and the indirect evidence has become so strong that basically the discovery becomes more of a relief to us in the field and a confirmation of expectations. The Higgs boson was in this category, which many of you I'm sure have heard about, an amazing achievement to be sure, but after the LHC turned on, its non-discovery would have been far more surprising than its discovery, at least to those of us who are experts in the field. On the other hand, there are discoveries that are completely unexpected, and the surprise of the discovery completely and very quickly changes the field forever. Sam's discovery of the charm quark was very firmly in this category. Now known as the November Revolution, if you read about it in textbooks and in the history of science, the charm quark was not only a completely new form of matter, similar to but different from the up and down quarks, which as you know make up all of atomic matter, but it fundamentally changed the field, opening the imaginations of scientists to what is possible. And I think it's really fair to say that that legacy has been felt very strongly even through all the decades since then, and is very much present in the field to this very day for all of us. I first met Sam over 2 decades ago in very interesting circumstances. Sam invited my then postdoctoral advisor, the renowned physicist Frank Wilczek, to talk at a big meeting of the AMS collaboration. Frank had a conflict and so couldn't attend, but recommended me. You know how most people would react to that sort of recommendation. Thank you very much, sorry you can't come, but there are a million people I'd rather invite than your little tiny postdoc who you just recommended. Okay, most people would not say that out loud or write that in the email, but you know that's what they're thinking. Sam didn't do that. He actually took Frank's advice for reasons I still will never understand and invited me. And so then, a few months later, I found myself on a plane going to Erice, Italy, a wonderful old science town, as an honored guest of the AMS collaboration. And once I got there, Sam treated me with far, far more respect than I deserved. It was just an incredible experience for me, one that I'll never forget. Since then, I have met many of Sam's junior collaborators, and it is remarkable how much he supports them, how much they respect him, and how they continue to work with him for years and years and decades and even entire careers. The experiment we were talking about at that meeting, way back in Erice, was known as AMS-1, a remarkable experiment that flew on the space shuttle for 10 days. Now, however, that experiment has been supplanted by the full AMS experiment, which is flown in space on the International Space Station not for 10 days, but for over 10 years. What has AMS found? Well, of course, Sam will tell us, but it turns out that empty space actually isn't all that empty. AMS has now detected over 215 billion cosmic particles and is transforming our understanding of the universe. As you know, particle physics detectors are really complicated things. They're some of the most precise scientific instruments ever constructed. And as you also know, space is one of the most inhospitable places to ever imagine to do a science experiment. So to combine these two is truly extraordinary. And if I were to try to sum it up for you, let me tell you a brief anecdote. When AMS was in its early stages, I remember talking to a senior colleague who told me, look, AMS is impossible, There are too many obstacles. It cannot be done. And then he gave me like 10 reasons, particular, why that was true. And then he paused. And then he said, on the other hand, never ever bet against Sam Ting. So please join me in welcoming Sam Ting to the podium as the 2023 Reines Lecturer to tell us more about AMS and his work exploring the cosmos.
Good evening. What I would like to do tonight is to share with you the experiment I'm doing at this moment on the International Space Station. This is an experiment I've spent about 30 years. In the past, I've always proposed my own experiment working together with large international collaborations. My first international collaboration, known as the Mark J experiment in Hamburg, Germany, leading to the discovery of gluons. And what is a gluon? When you have an atom inside the nucleus, there are protons and neutrons. And inside the proton and neutron, there are quarks. What bound the quarks together are gluons. And so this was supposedly an important discovery. So this was the early days for the experiment in Hamburg, and there's me together with 3 German collaborators. And this whole electronics, now you can put it on your iPhone. This was an important work, and there's a full page in the New York Times explaining this work. My second international collaboration is known as AIR-3 experiment, which lasted 20 years, involving 20 countries, including United States, Soviet Union, now Russia, China, Taiwan, India, Pakistan, and different European countries, using 100 billion electron volt positron collide with 100 billion electron volt electron. Susan and I lived here. So this is not a small experiment. It's 6 stories high, and the detector weighs about 10,000 tons. One of the experiment result is concerning neutrinos. Neutrinos was proposed in 1930 by Wolfgang Pauli. It's a chargeless, massless particle. In 1956, electron neutrino was discovered by Fred Reines and Clyde Cowan. In 1962, Lederman, Schwartz, and Steinberger discovered a new kind of neutrino. In 2000, a third kind of neutrino was discovered in Fermilab. A question you ask, how many kinds of neutrino exist? So in this experiment, we found a model-independent way to determine number of neutrino species by looking for positrons, electrons collide, produce neutrinos, and measure gamma rays. By measuring gamma ray, this is our data. This is central mass energy, and this is if there are only 3 kinds of neutrinos. So what do we determine? Indeed, within the current energy range, There are 2.98 plus minus 0.064 number of neutrino species. Our current international collaboration is the Alpha Magnetic Spectrometer on the International Space Station. It consists of people from MIT, from NASA, from University of Hawaii, from Maryland, from Mexico, Brazil, Italy, Spain, Portugal, France, Netherlands, Finland, Germany, Turkey, Switzerland, Italy, Russia, China, Korea, Taiwan. What is unique about this collaboration is the fact none of them have ever done an experiment in space. So we started from totally a clear head, meaning you have nothing, knows nothing. I remember in 1994, after the close down of superconductor and super collider, I was walking in my garden and asked myself what I should do. I just finished this L3 experiment. Then I decided I've been spending a lot of time in accelerators. I really should do something new, something I know nothing about, something everybody thinks is not possible. That's it. The highest energy particles are produced in cosmos. The largest accelerator on Earth produces particles of 7 trillion electron volts. Cosmic ray with energy above 100 million trillion electron volts has been detected. This is the pure Auger experiment with an area of 3,000 kilometers square in Argentina. We will go to space to measure electrons, positrons, and nuclei up to multi-trillion electron volts, something you cannot do underground. So using the current language, we will look for physics of dark matter, antimatter, the origin of cosmos, and new phenomena through the precision, long-duration measurement of charged cosmic rays. Charged cosmic rays have a mass, and therefore they are absorbed by 100 kilometers of Earth's atmosphere, which is equivalent to 30 feet of water. So the property, like its value of the charge, the sign of the charge, and the momentum of charged cosmic ray cannot be studied on the ground. On the ground, you can measure the total energy from cosmic ray interact with the atmosphere. To measure cosmic ray charge and momentum require a magnetic spectrometer to measure the charge and measure the momentum. But put a magnet in space has a fundamental difficulty. Everybody remember the magnetic compass. One end will be point to the north, the other end point to the south. So if you put a magnet on the space station, soon the space station will lose control. And that's why people didn't put the magnet in space. And we figure out a method to make sure this magnet does not rotate. Discovery from cosmic rays and foundations of particle physics. Let me share the example. Discovery of positive charged electron by Carl Anderson, and discovery of pi meson by Paul, and discovery of cosmic neutrinos by Koshiba. Before the development of high-energy accelerator, discovery of charged cosmic ray laid the foundation of modern physics, including all the early discovery of elementary particles. In the past 100 years, measurement of charged cosmic ray by balloons and satellites are typically have a 30 to 50% accuracy. AMS is providing cosmic ray information with 1% accuracy. The improvement in accuracy and the extension of the energy range is providing new insight. As I will share with you, none of the results can't be explained by the current theoretical models. So you require the development of new model for the universe. Cosmic ray was discovered in 1912 by Victor Hess, and this is some of the results, key results from different cosmic ray elements over the last century on lithium nuclei, beryllium, boron, nitrogen, fluorine, sodium as example. And you can see before AMS, the dotted line is theoretical model. The vertical lines are different experiments. The theory is in good agreement with the experiment, mainly because the experiment error is so large. With the AMS, you can see the yellow point is the AMS measurement, and the blue line is the same theory, so none of the measurement agrees with the model. When we started the experiment, there were many concerns, and I got this cartoon that we are not exactly rocket scientists. In fact, I know nothing about space when we first started. Because of that, NASA said, maybe you have a good record, but you know nothing about space. Space is very hostile, very expensive, and you need to prove yourself. So they asked us to build first detector, put on the space shuttle for 10 days. So it was approved in 1995. We managed to assemble it in December 1997, despite NASA's estimation it would take us 10 years. And we flew for 10 days in 1998. Most difficult part is the magnet, because nobody has done a magnet before. And so we actually have 10 magnets built. 7 of them is to verify the design, make sure there's no fuel leak out, make sure the magnet do not rotate. The magnet was made in the Institute of Electrical Engineering of Chinese Academy of Science in Beijing. The reason it was made in China is because the best permanent magnet material is from Inner Mongolia, which at this moment is part of China. And that's why the magnet was made in China, and they did an excellent job. Then we built 3 full-size magnets. One is to do acceleration and vibration, simulate the shuttle lift the ground. And second is to see under what condition the magnet will fall apart. The magnet has 4,000 pieces of permanent magnet material. The force between them is 4 tons. If during the shuttle lift the ground, if one piece go out, will destroy the shuttle. So we better figure out beforehand. And so we build a magnet, try to destroy it. Turn out we cannot destroy it. The third is a flight magnet. So the magnet manufactured in China with close verification by NASA engineers, and to see every step fits to the NASA standard. And this is an important test. This coil simulates the Earth's magnetic field, generated field, simulate the Earth's magnetic field. And this is the 1/3 size of the magnet. And if this turns, means everything's wrong. In fact, this does not turn, means there's no torque. So these are the 5 astronauts come to have a discussion with me in my office at CERN. And this is assembly of the magnet in Kennedy Space Center, and this is AMS in space for 10 days. Because the precision, everything you see is surprising. One of the most surprising results is helium in low Earth orbit. In the energy range between 100 million electron volt to 4,000 million electron volt over a large region, namely plus minus 35 degrees with regard to equator. All the helium are isotope helium-3. Helium-4 is outside the equator region. Now, outside the equator region, there's helium-4 plus 10% helium-3. But in the middle, it's only helium-3. It's a very strange phenomenon. Nobody knows why it is like this. After the successful engineering flight of MS-01, we received strong support from NASA and from all the collaborating institutes to proceed with the MS-02 mission on the space station. So in the following presentation, I will refer MS-02 simply as MS. MS-01 weighs 9,200 pounds. After finished, after many discussions, finally I made a decision, threw everything of MS-01 away, build the most precise detector possible. And therefore, with the exception of the magnet, everything we built with state-of-the-art detector with 15,000 pounds. So MS is a space version of a precision detector used in accelerators. On top is something called transition radiation detector. An electron or positron goes through, will leave a signal. Then there are 9 layers of silicon tracker, measure the charge and momentum. A rain image Cherenkov counter, measure the charge and energy. An electromagnetic calorimeter, measure the energy of the electron positron. 2 banks of time-of-flight counter, measure charge and energy. And then there's the magnet, together with the rest of the detector, measure again the charge and energy. And there's a bank of counters when particles go in from the side are registered and rejected. And you notice charge and energy are measured multiple times. And this, of course, is not a cheap detector. But if you want to do an experiment of this type, then you need to realize you only have one chance. Once in space, if it doesn't work, there's no way for you to repair it or replace it. And so you need to do the best you can. So after the detector was approved by the US government, the Department of Energy, which normally support me, said, good, this is a very good experiment, but we also have no money. And so we have, fortunately, large international collaboration. So detector was constructed in Europe and Asia, assembled and tested CERN and European Space Agency with NASA support. 10 years ago, NASA estimated the cost of this detector was about $2 billion. The US contribution is about 5%. The most important support from US Department of Energy is not financial, but it is the organization of a blue ribbon panel review of MS science by distinguished scientists, Nobel laureates, member of the Academy of Science, and astronauts. The first meeting was 1995, and with the participation of Barish and Smoot, the one marked in yellow are Nobel Prize winners, and the last review was just about a little more than a year ago. After the Columbia accident in 2003, NASA decided to retire the shuttle and cancel all the science flights to the space station. By then, we were halfway through Nevertheless, the experiment was strongly supported by the science community. And this is a letter from the Undersecretary of Science from DOE to Michael Griffin, the administrator of NASA. He says, "It gives me great pleasure to forward to you the scientific panel report. It constitutes one of the Blue Ribbon, from the Blue Ribbon panel. AMS is an important mission for DOE. We continue to support AMS for its scientific panel and strong international collaboration." Namely, what DOE is saying is to NASA is, even if you cancel the project, we're still going to support it. And then at that time, there were many, many articles, and this article from New York Times, long-awaited cosmic ray detector may be shelved. And there were remarks from George Smoot, from Barry Barris, and others. And Steve Weinberg, a distinguished physicist, wrote an article about science of spacemen, and also made a cartoon, and there's a coffin with the AMS in it. And Steve Hawking, whom I've known for many years, made a special effort, brought his medical team of 11 nurses and spent the whole afternoon in the MS Assembly Hall and had a conversation with me. I think this was his last visit to CERN. It was very difficult to talk. Recently, Susan and I went to Westminster Abbey and we found his grave. It says, "Here lies what was motto of Steve Hawking," and this is the black hole formula. A truly remarkable person. And finally, unanimously, the House and Senate passed a resolution, HR 6063, requests NASA to provide an additional flight to deliver the Alpha Magnetic Spectrometer and other scientific equipment to the International Space Station. So let me share with you how this detector is built. This is transition radiation detector made out of 5,000 tube detectors. The tubes, each 2 meters long, and there's a signal wire, 100 micron in diameter, made out of gold-plated wire. And once you put the wire in, you need to center them. And to center them, one of the professors in our group, Professor Scher, who was then the Dean of Science, he said, now the best way to do it is treat them as patients. Go to the hospital, go to the university hospital, and so put them in the CAT scan machine and make sure they are centered. So 9,000 tubes were built, 5,000 were selected. And this is the installation with 1 cubic meter in volume of the transition radiation detector on top of AMS. We have collaborated with the Germans for many, many years, because I started my career working in Hamburg. And so there's RWTH Aachen, Karlsruhe, Max Planck Institute, and many industries. And occasionally, I go to the universities, give them a report, what is going on. And they have very precise machine shops which manufacture many of our instruments. And then the silicon tracker provides a coordinate resolution 5 to 10 microns and measure momentum and nuclear charge. And there are 9 planes. And this is a large international collaboration because the accuracy needed. So it's done under a microscope, and they're mostly done in Switzerland and Italy. We have a national effort from Italy with universities and with national laboratories. This is a rain image Cherenkov counter. It's made out of 10,880 photosensors and measure nuclear charge, velocity at the speed of light to an accuracy of 1 in 1,000. And these are made from Spain, from France, from Portugal, from Italy, and from Mexico. For all the detectors, you always make two. One for test to the acceleration and vibration. Once you have done that, you do not know there are cracks or not. And so you don't dare to use it again. The second one is for flight. And if you have doubt, you make another one. The electromagnetic calorimeter are made out of lead foils with optical fibers, and some optical fiber in the X direction and some in the Y direction. So when the electron positron goes through the lead, it loses its energy into shower. The shower is measured in the X direction, in Y direction, as well as in Z direction. In total, there are 50,000 fibers distributed uniformly in 1,200 pounds of lead, so provide a radiation length of 17 radiation lengths. So it provides a three-dimensional measurement of energy and direction up to 2 trillion electron volts. The mechanical structure to support this was made by the Chinese. The flight electronics total, just a minute, of 300,000 channels, provide 3.7 megabit per event at a rate up to 2 kilohertz. So in total, there are 7 gigabit per second processed by 650 computers to 10 megabit per second down the ground. And this electronics is from commercial element and very, very fast and not from military grade. So what do we do? So the procedure is to transform particle physics electronics for use in space. And this is really developed by the MIT group. And first, you make prototypes, and prototypes you subject it to radiation, to acceleration, to vibration, to vacuum test, then you make an engineering model. After an engineering model, you do the test again, you make a qualification model. And then you do the test again, you do the second qualification model. Finally, you have flight model and flight spare. So to get one board working on orbit, you need to make 10 boards on the ground. In total, 464 boards on orbit of 70 different types. So it's a rather large effort. And the electronics was designed at MIT but manufactured in Taiwan. The group performed extensive radiation tests to select components that tolerate radiation of space. We do tests in Italy, in Switzerland, in Indiana, as well as in Germany. So this is the final detector, 5 meter by 4 meter by 3 meter, weighs 7.5 tons. After that, we must make sure it will work in space. And so we'll do the electromagnetic interference test in the European Space Agency Test Center in Holland, and to make sure our signal does not interfere with NASA, and we can get our signal. I also want to make sure it works in vacuum, and at 10 to the minus 9 bar, and the temperature goes from minus 90 degrees C to plus 40 degrees C. To do this test, we do receive very strong support from the European Space Agency, and this is a letter from the head of the European Space Agency, said, I confirm that I grant highest priority to MSO2 in providing access to STEC Center as soon as possible. And then, after that, we put the detector in the accelerator. to make sure it really behaves as it's designed. And to do that, CERN actually shut down the main accelerator and just do the test for us. And there's a letter from the head of the accelerator group that there is a decision from directory level to give the maximum possible amount of help to AMS. And then finally, when we finished the detector, the detector is too large to be put into a Boeing 747 Lufthansa cargo. And so, fortunately, the chief scientist of the Air Force was a physicist. And so I went to talk to him, and they offered to send a C5 from the United States to Geneva and to able to load us to take us to Kennedy Space Center. And people in Geneva had never seen such a large airplane, so made a headline in the local Geneva newspaper. The airplane is so large, when it landed in Kennedy Space Center, there was actually an officer stick his head out to make sure the wings do not touch anything. So we were in Kennedy Space Center for about 6 months, doing all the final tests. And one night, I was in the launch tower alone for about four hours. I was just thinking. I was involved in all the discussions and decisions for the last 16 years. Many of the things I really do not know. Is there a mistake? Could there have been something I have forgotten? And so, because if something's wrong, you must not let it go. Once you let it go, and there's nothing you can do. And so after 4 hours, I remember I left and my whole hand was cold. I was rather tense, rather worried what may happen. And so this is May 15th, just before launch. And the night before the launch, the astronauts invited me to their quarters together with their spouse for a dinner. I did remember, I still do remember, the food was very good. And so I offered to help to support NASA by putting their shoes on. This is now the senator from Arizona, Mark Kelly. So 2 days later, the space shuttle approached the space station. And after they installed AMS on the space station, and they had a rather lengthy conversation with me, actually, I do not know their terms. It's hardly for me to understand what's going on. But I remember my first sentence to Mark was, "How come you're upside down?" He said, "No, you are upside down, because this is a relative." So now, for the last 11 years, our signal goes to a Tetra satellite, goes to White Sands, and go to a payload operation control center at CERN. At CERN, we have an exact duplicate of the electronics on board. So if there are anything you are suspicious, you test it here first before you send on board. 2 months before we sent to space, I suddenly realized there's a very complicated communication channel. What happens if the channel breaks down? And so I request to NASA to install a PC or a little computer on the crew quarters. And the little computer costs a few $1,000s, but if you want to put in space, you need to add 3 more zeros behind. So now all the astronauts knows how to use this computer. Indeed, often the communication breaks down. So this is the control room. This part is talk to NASA, talk to the space station. This part is looking for the detector performance, and this part is to look at the thermal conditions, because it rotates around the Earth every 93 minutes, the temperature changes greatly. It is fully staffed 24 hours per day, whole year round. And during the COVID time, this had not been easy. Once in space, you must assume that something may go wrong, and you really need to monitor all the time. If something goes wrong, and you know where it goes wrong, then you can correct it. If something goes wrong, and you do not know, and then you're going to make a mistake. So let me share with you the detector verification, like the tracker alignment. There are 9 planes of tracker. Inside plane aligned to less than 1 micron with 20 lasers. The outside plane, the layer 1 and layer 9, aligned every 2 minutes by cosmic ray to an accuracy over 10 years of 2 microns. So it's highly accurate, it's always monitored. So the detector provides independent and redundant measurement of momentum of particle, sign of charge, rigidity. Rigidity is a term known as momentum divided by charge, energy, and flux. So this is the measurement from the scintillation counter and from the silicon tracker. The correlation shows the distribution of all the measurable particles. So these are the correlation of 2 detectors. If you put all the ability of 5 detectors together, you have a clear separation of all the cosmic ray elements. To the accuracy, look separate between hydrogen and helium to 1 in a billion. And so you now have clearly separate all the elements, and you know now for the first time what is going on in the space of cosmic rays. So let me share with you a few of the results. Why is property of cosmic nuclei? Cosmic nuclei are classified into 2 classes. Primary cosmic rays are produced in stars from nuclear fission process accelerated by explosion of stars, such as helium, carbon, oxygen, silicon, iron. Secondary cosmic rays are produced by collision of primary cosmic rays with interstellar medium, such as lithium, beryllium, boron. Indeed, on Earth, all the lithium, beryllium, boron are from space. Study the property of cosmic nuclei will probe their origin, acceleration, and how they propagate. So this is the measurement of primary cosmic ray for helium, carbon, oxygen, neon, magnesium, silicon as an example. The red point is the MS measurement, the yellow dots are the theory, and the large vertical line are previous measurement over the last century. What do we learn from a graph like this? The first thing you learn is unexpectedly, above 60 GeV, the light primary cosmic ray, helium, carbon, oxygen, have identical rigidity dependence. They go flat to 200 GeV, go up together. And these are based on millions to 100 millions of events. There's no reason, no theory to say all these cosmic rays should have the same rigidity dependence. Yet, this is what we see. The second surprising result is heavier elements, neon, magnesium, silicon, have their own rigidity dependence, and they are different from the light cosmic ray. Helium, carbon, oxygen have this dependence, and neon, magnesium, silicon have this dependence. Namely, primary cosmic ray have at least 2 classes. Why? Nobody knows. It's a new observation. So the American Physical Society once in a while select from their publications results shown to the press, and these are written by American Physical Society. We have no input. It's a long article, but let me quote one sentence. The results now give theorists a lot of work to do, and they are opening an entire new window on precision cosmic ray spectroscopy, says Peter Biermann of the Max Planck Institute for Radio Astronomy in Germany. We can now turn stars into high-energy labs, which the universe is running for us. Then we look at iron. Iron is a very important element in cosmic ray theories because it is the heaviest element produced during stellar evolution. Iron has a large interaction rate with interstellar medium and come from closest part of the galaxy. That is because iron has 26 protons, 26 neutrons, so it has a large size. So it's easier to interact with interstellar medium. And those survived must have come from us. Helium, on the other hand, has only 2 protons and 2 neutrons. And so you can come from far away. So the question is, what is the difference between helium and iron? We found iron, it's no difference with helium. Iron is in helium, carbon, oxygen, primary cosmic ray group. And instead of the expected heavy neon magnetism silicon group. You will imagine iron being so heavy should belong to this group. No, we found actually belong to this group. So now we have measured 8 elements, and they can be grouped into 2 groups: helium, carbon, oxygen, iron, the yellow band, and the blue band, neon magnetism, silicon, and sulfur. Secondary nuclei measured before AMS on lithium, beryllium, boron, and fluorine. These are very difficult to measure, and therefore the errors are awfully large from previous experiments. The red one is all results. Again, has nothing to do with theoretical model. What is most amazing is for secondary cosmic ray, you also have 2 classes. Helium, lithium, beryllium, boron, the rigidity dependence exactly on top of each other, goes down and then turns. Fluorine is different. So secondary cosmic ray also have 2 classes. Now let me share with you some latest results on positons, electrons, and antiprotons. They can only have 3 sources. One is ordinary cosmic ray collide with each other, produce positons, antiprotons from collision. So these will always exist because cosmic ray travel, and they will meet each other, they will produce positons, antiprotons. If there is dark matter in particle form, and when they collide, they produce energy, and energy can become positons, antiprotons. Or as rotating neutron star, pulsars. Pulsars can produce positons. So this is the measurement of positons and electrons before AMS, and has a very large errors, and you cannot make too much sense out of positons and electrons. This is the AMS result, 50 million electrons, and show in this axis, and 3.4 million positons in this axis. And you know they're totally different from each other and not related. So what is the origin of positon? The positon flux is the sum of low energy part from cosmic ray collision, which you can calculate. Indeed, they agree with the measurement. And plus a high energy part. The high energy part must come from the remaining region, namely pulsars or dark matter. But the error is still very large, and that's why we'll continue taking data. But what is more important is the spectrum goes up. It does not continue to go up. It goes down. And so you have a cutoff energy. The cutoff energy is close to 5 sigma, and namely 99.999%. And this is a totally new, unexpected phenomenon. Why the positron spectrum goes down? The electron spectrum come from two power law, one power law A, one power law B, and one term from the positron axis. And so the high energy part require a positron source term. That means there is a source that produces equal amount of high energy electrons and positrons. Only pulsar or dark matter will do that. And this is based on 50 million events over a wide energy range. Positron from pulsars. Pulsars can produce positrons and accelerate them to high energy. A light ray interact with a strong magnetic field, produce electron-positron pair. Both of them can accelerate to high energies. But a light ray does not produce proton-antiproton pair because the mass is so heavy, and therefore you do not see antiprotons. Positron also can come from dark matter. 90% of the universe is not observable, that this is called dark matter, mainly because you cannot see it. And this is a galaxy we're familiar with, seen by the telescope, and this is a galaxy imagined if you could see the dark matter. Positron spectrum from dark matter collision, if you have dark matter collision, you produce positrons and antiprotons. Dark matter with a mass m, conservation of energy and momentum require the positron energy must be smaller than m. And so there's a sharp cutoff from spectrum for positron and m. And this one of the early paper, a very important paper in Physical Review Letters by Jonathan, and shows the spectrum depends on the mass of dark matter, always will have a cutoff. This is our measurement. Yellow point is our data. The blue is one of the dark matter model with a mass of 1.5 trillion electron volts. You do see a cutoff, sharp cutoff. But we want to reduce this error to make sure, indeed, it is going like so. We also measure antiprotons. Antiproton to proton ratio, this ratio, show that about 60 GeV, the ratio is energy independent. The antiproton to proton ratio cannot come from collision of cosmic rays. Collision of cosmic rays produce this curve. And what we measured at the yellow point, that means there's a new source produce antiprotons. The origin of cosmic antiproton is unknown. But what is known about the antiproton is the antiproton and positron flux have identical rigidity dependence. And you can see positron spectrum and antiproton spectrum, they behave very similar. Antiproton cannot come from pulsars, and therefore most likely positron also cannot only come from pulsars. Now, let me share with you some latest data on antimatter. Paul Dirac received the Nobel Prize in 1933. And based on the observation, the equation of motion in relativity and in quantum theory, mass appear always in square, meaning it can be m times m or minus m times minus m. Dirac asked, what is minus m? Lead to the theory of antimatter. So for a real good physicist, getting a Nobel Prize is quite easy. In his Nobel lecture, he said, if we accept the view of complete symmetry between positive and negative electric charge, so far as concerned the fundamental laws of nature, we must regard it as rather accident that the Earth contains mostly of negative electron and positive proton. It is quite possible that for some of the stars, it's the other way about. These stars being built mainly of positons and negative protons. Negative proton, known as antiproton, indeed was discovered in 1955 by Segre and Chamberlain. So in 1965, among my earliest experiment, which was announced in the New York Times, is the discovery of an antiproton, anti-neutron bound state of antideutron. This was a difficult experiment because the signal to background is 1 in 100 million. This is an important experiment, not in physics, but for me personally, because this little report was translated in Beijing in a newspaper article. And this translation, I think, is completely wrong, because I couldn't understand it. But they did make the remark about me. And then my family in China know that I'm still alive and actually a physicist. So now, if there are antimatter stars, there must be anti-deuterium, anti-helium, anti-carbon, and anti-oxygen. Matter is defined by its mass and charge. Antimatter has same mass but the opposite charge. To measure this, you need a magnetic spectrometer to identify the charge. And so you need a magnet. So this is a unique antimatter spectrometer in space. This is an anti-deuterium candidate from 100 million deuterons and 10 billion protons. It shows in the production plane, in the non-bending plane, looking from the top, measure the Cherenkov cone. And this event has a charge -1, plus minus 0.05. Mass is the same as deuteron, but the charge is just the opposite. So it's anti-deuteron. And then this is an even more rare event, anti-helium. 2 antiproton, 2 anti-neutron combined together. And this is in the bending plane, in non-bending plane, and measure the speed. This charge is -2 plus minus 0.05. The mass is exactly the same as helium-4, except helium-4 has positive charge. Most people think this that cannot be found, cannot exist, yet we do see them. So when I first went to space, there was a little article in Scientific American about its potential. In 11 years on the space station, we have recorded more than 216 billion cosmic rays. The accuracy and the characteristics of the data simultaneously from many different types of cosmic rays require the development of a new model of the universe. We'll continue to collect data to 2030 with upgrade of the detector. About a year ago, I thought maybe we should improve the detector. So here's what we're going to do. we're doing it now. This is the current detector, and this is the silicon detector. What do we want to do? So add a new silicon layer, 4 square meter, and finish in 2005. And so from 2005 to 2030, there are 5 years. The upgrade will increase your acceptance by factor 3. So 5 years become 15 years. You collect more data. So what is the physics of upgrade? The upgrade will enable us to measure to 1% accuracy the elements marked in white. These elements we have not analyzed because they still carry about 10% error. So we want to make sure we'll have a 1% error to all the measurable cosmic rays, and therefore settle down to look for a model can explain all the data. So far, it doesn't exist. Another thing, of course, is dark matter. I mentioned the magenta line is the dark matter, one of the dark matter model, and the yellow data is the MS measurement. The error is still very large. And we want to reduce the error by collecting more events and have the light blue line, and therefore make sure it's in agreement with one of the dark matter model. And more important, to see this point. At this point, there's no more dark matter contribution, only from cosmic ray collisions. Our most favorite topic is antimatter stars. In 11 years, we have measured for matter 50 million electrons, 7 billion protons, 1.3 billion helium, and tens of millions of different nuclei. For antimatter, 3.4 million positons and 800,000 antiprotons. These mostly come from ordinary particle collisions. We see anti-helium signal, and then question is, where is anti-carbon, anti-oxygen? To do this, it's not exactly easy because the area is very large, and so we need a rocket and use SpaceX Dragon to bring us up to the space station, use a mechanical arm to pick it up, and then transfer with the mechanical arm to on top of AMS and install it. This can be done mechanically, but you need an astronaut to connect all the thousands of cables. And so we recently I sent 2 astronauts out to look there enough space to connect the cables, and turn out to be just lucky. Turn out to be there's enough space. Because when we started the experiment, we certainly didn't think about this. So the result from MS are unexpected. We'll continue to collect data over the lifetime of the space station, and this will change our understanding of the universe. But to me, the most important goal is to explore the unknown, to search for phenomena in nature that we have never imagined in order to discover. Thank you.
Well, thanks. Thank you so much, Professor Ting. That was wonderful. We do have a reception that we're going to offer in a couple of minutes, but we do have time for a few quick questions. My understanding is we have some microphones. Is that right? So if anyone has a question about anything at all, you can raise your hand, and then we can wait for the microphones, and I'll try to point out where we're going to go. Why don't we start right here, and then we'll move down here.
Yes, thank you for your talk. For the layman, can you just define what is rigidity dependence? I don't understand that.
Rigidity is a term I didn't know before either. It's not used in accelerator. Rigidity is momentum per unit charge. For proton, charge is one, namely one proton. So momentum, energy, and rigidity are exactly the same. For helium, you have a momentum of 1,000. The charge is 2. The rigidity will be 500. Momentum divided by charge. It's a term not defined by me. Please.
It seems like AMS has detected an dark matter particle with a mass of 1.5 TeV. So can you talk a little bit more about that? And are there any dark matter candidates at that mass?
The candidate is what I just shown. And there are 3 ways to look for dark matter. One is collision, like proton-proton collision, produce dark matter. Well, actually, Jonathan was the first one to point this out. In Erici, you were mentioning Erici. Another is dark matter collision, produce particles, like positrons, antiprotons. And that's what we are doing. That's just the opposite of CERN doing proton-proton collision. Another is dark matter decays and detected interact with the nuclear underground. You do underground recoil measurement. So there are 3 classes of different methods. All methods complementary, independent of the 2 previous methods. Which one will get it, you do not know. So far, our data is in agreement with dark matter or mass about 1.5. But this does not mean we have seen dark matter, because the error is very large. And this is why we're taking this unusual step to upgrade the detector in space.
Thank you.
We have a question in the middle here. I think
Hi, Professor Ting. I have a question about the positron spectrum. So in the high energy positron spectrum, you see a higher flux. However, the systematic bar is larger in the high energy part. So may I know why? Is it because of the acceptance or the size of AMS that cannot have a high efficiency in the
The spectrum is not due to detector. It's due to nature. It's not because of acceptance. The acceptance is the same with low energy part and high energy part. It's a very large acceptance. It's totally uniform. If you have a very small acceptance that's energy dependent, you're not going to measure anything.
So then a follow-up question. So if you increase the AMS, the size of AMS, so it is possible to improve the detection efficiency in the high energy positron part.
You increase the acceptance uniformly as function of energy. Never choose one part to increase. Then you're going to make a systematic mistake.
Thank you.
Yes.
You mentioned that the AMS-1 found that the distribution of the helium-3 was primarily over equatorial regions versus helium-4 on the outside. Was that borne out by the AMS-2 in the shuttle, and any ideas why? I'm sorry, the AMS-2 on this
Both
ISS.
AMS-1 and first was seen by MS-1, and then confirmed by MS-2. When you flew over the equator, you only see helium-3. When you go to the North Pole, you see helium-3, helium-4.
Okay.
Very strange phenomenon.
It is. I guess that's under the path of the moon, but who knows?
No, yeah, these are very high energy particles, trillions of electron volts. Yes.
Hi. How are you detecting the antiprotons? Because would think when they'd hit the detector, they'd annihilate with the protons within the detector.
Yes. Antiproton annihilate with proton. And this was the first observation of antiproton in 1955. And later on, people think this is not a good method, and that's why Segre and Chamberlain use a magnetic spectrometer. For us, what you said is exactly right. In order to make sure the antiproton do not annihilate in your detector, the detector must be very accurate but very, very thin. So the detector is why it's so expensive, is you want to make it very, very thin, but very accurate. So you repeat the measurement part by part, make sure they're all consistent.
So I think we have time maybe for one more. We have one last question.
Yes.
You mentioned that all the detectors elements were chosen to be radiation hard. Did you see any degradation of the detector over the 10 years?
Over 11 years, nothing has went wrong. No detector, no element has stopped. But independent of that, the key electronics will have a four-fold redundancy because you cannot go there to fix it. So instead of making one, we'll make four. You will automatically switch, but that has not happened yet. But this does not mean it will not happen tomorrow. In fact, most of my time is staying in the control room, watching the response of the detectors. It's very important you be suspicious what could go wrong.
Okay. I think we could probably go on for a while, but I think now would be a good time to let Professor Ting rest a little bit, and we can move out to the reception. Let's just take this opportunity to thank Professor Ting one more time.